Hi everyone. So I'm going to present some work that I've been doing with Laurence Tratt over at GCed. I understand that this is perhaps a bit of a controversial subject in Rust. Many of the Rust programmers in the room here might be wondering why on earth do we even want garbage collection in Rust? And even the part of the selling point of Rust is that it doesn't even have garbage collection, right? This is slimmed down, you don't want it. But what I'd like to show really in the next 10 minutes is that when you get to the edge of the ownership model, you end up in this place where there are certain data structures that are very difficult to express. And Rust programmers will probably be aware of this in that when they want to deal with things like cyclic data structures, they end up writing either reference-counted data structures or they use arenas or some sort. And what I'd like to show really is that another thing that can fit in here is garbage collection as a sort of opt-in tracing GC for particular areas of memory that you'd like to manage. And not only is it possible, but it can be done in a pretty ergonomic way that a lot of Rust programmers will be familiar with if they use things like the standard libraries reference counting. But also that we can kind of address some classical GC problems this way because of Rust's unique type system. The title is a bit of a spoiler, but these are really to do with finalization. And I'm going to go over hopefully one or two little examples of how this will work. But it's probably best to start with a little demo. So I'm going to make this a bit bigger so people can see it. Is that okay? Everyone see this? Yeah, great. Okay, so what's going on here really is that we've got this small graph and it's managed by reference counting. So we've got this cyclic data structure, we have this node and a next pointer, and that next pointer is using an enum to determine whether it's a weak or a strong reference. Of course, this is reference counting, so the back edge needs to be represented using a weak pointer. So we construct these nodes, we link them together, we make sure that we downgrade to a weak pointer for the back edge. And that means that if we want to go and traverse around this, then we have to do this sort of boilerplate dance, really, to determine, well, is this a strong pointer, is this a weak pointer? And if it's weak, we need to deal with it in some way. And you can see that this is a bit of a sort of trivial example, but if you blow this up to graph-like data structures that are pretty large, this gets a little bit unwieldy to deal with. So what I'm going to show you now on the other side is, I'm going to make this a little smaller so you can see them both together. This is how you would do the same in GC. So this is the GC that we've written here is called Alloy, and Alloy provides a GC smart pointer type, a bit like the RC type. And you can see it's very similar here in that you construct your graph just using this GC type. You link the nodes together. Notice there's no weak pointers for this. Everything can be a strong pointer because it's using tracing GC under the hood. And there's a couple of key differences, really. So the first is that you don't clone the reference counted pointers anymore because there's no need to incref or decref. And that means that there's no need for a drop method to do the decref at the end when that goes out of lexical scope. What I have shown here is a little drop method that just prints what's happening for the node here. And because this is GC, this will be run as a finalizer when that's unreachable. So what we have here really is context-dependent drops. So if they're used inside a GC, then those drop methods will be run as finalizers. Otherwise, they're used sort of as your regular Rust-style destructors. And because tracing GC makes this stuff quite a lot easier, or more ergonomic to write, there's definitely like prior art that has explored this space quite well and come up with some really cool ideas. What I want to hopefully show you really is why Alloy, our GC, is a little different. And I go over three main points that kind of show this. And the first really is that Alloy is a conservative garbage collector. So unlike the others, which try in some way to provide an API for the user to precisely identify the root sets for GC, Alloy takes the opposite approach of saying, well, if something looks like it could be a pointer, then we'll treat it as such. And this has obviously the downside that it could over-approximate the root set in some way. The reason that we do this is that precise GC usually requires some restrictions on what you're allowed to use that garbage collected type for, right? So what we noticed is that you're either restricted in what you can GC or when you can run the GC, or you end up having to limit your Rust program as a whole to use a sort of subset of the safe language. That sounds a bit abstract, so here's a very simple example. What we have here is a simple pointer to, a reference to unsigned integer cast. So essentially what we're doing really is we're stripping away the provenance of that pointer. This is not ideal. We don't really want to be doing this, but this is possible to do in safe Rust code, right? And in safe Rust code, it only becomes unsafe when later on you want to go and dereference that. So why does this matter for a GC? Well, the GC needs to be able to know exactly where those pointers are at some arbitrary point in time. It's not actually just when you access that pointer in the mutator at some point. The GC is now this sort of thing running in the background that our Rust application never knew about. So this is something that we've got to deal with. And some of you might be aware that there are lints in recent versions of Rust that actually track strict provenance. So they don't really allow this, or rather they tell you not to do this. It's still possible to do. But even if we were to solve that, there's some other issues in the language where this becomes problematic. But also, Rust, the compiler, the toolchain, is an uncooperative environment, the GC, right? So if you have this precise bookkeeping information that you're tracking, the compiler doesn't know about it, and you have to go through and somehow change your optimization phases to make it aware of this in some way, which is not really a small task. I should also mention, rather, that there are issues with conservative GC itself, and yes, you do have to restrict some parts of what the language can do too. The main thing really is that you can't obfuscate those pointers in any way. So that precludes things like XOR lists from being written in GC with, a Rust program with Alloy. But what we sort of found empirically is that the restriction that this imposes is less burdensome than perhaps some of the others that would be required for precise GC, especially because some of the things that you see in the standard library are things or are sort of patterns in Rust that the precise GC approaches would not be able to handle. So moving on really from conservative collection, Alloy was designed to be retrofit to existing programs, right? Conservative collection makes this a lot easier because it reduces the API service that needs to change. But there's a couple of other things. So I mentioned earlier that what we do is we take existing drop methods, turn them into finalizers when we can. And by doing this, we were able to take some mature existing Rust programs and convert them to use GC. So these programs here all in some way had reference counting for various parts of their internals, and we've replaced those where we could with garbage collection. Now what I should say is that in some of those it wasn't possible to do a whole translation because they relied on the semantics of reference counting that was not possible with GC. But for the most part where we could, we were able to convert them. And what we show here is just sort of one of quite a few experiments we did. And I'm just trying to highlight here really that on average, if we use the average heap that comes with Alloy, then you're looking at around about 10% slowdown and maybe 1 to 2x of the memory consumption. Obviously, we do allow you to set a minimum and maximum heap, so you can change this calculus somewhat, but this is with the defaults that sort of grow and shrink as necessary. And finally, finalization. So I did allude to this earlier. This is the main issue that we found when we were dealing with this, this conversion. But one of the things to know is that in Rust, what could be a safe drop method, i.e. what could be safe to do at the end of a lexical scope, is not necessarily something that's safe to do at some arbitrary point in the future as part of a finalization of an object. And a lot of the cases that we found around this were to do with, in some way you have a reference that's managed to linger for longer than the object has stayed alive. And because with our GC, we want to say to people, if you use it in safe Rust code, you get a safe GC. Finalization is a sort of backdoor to break these safety guarantees. And so we needed to address these in some way. And we did this using something called Finalizer safety analysis. And essentially what this is a static analysis pass that we added to the Rust compiler that looks at the control flow graph of the intermediate language. And for every drop method, we check, is this doing something that would be dangerous in a finalizer? And so there's quite a few different possibilities where that could be the case. But in general, what we found is that even though this over-approximates, we're able to get quite granular to be usable in real programs. And where it's not, the user can say, here's an escape hatch, I know what I'm doing, let me do what I want to do, please. So in the interest of time, we've only got a couple of minutes left, but I do want to just quickly show you how this might look. So here's a simplified version of the code I showed you earlier. I've just removed a couple of the nodes and some of the types in between because I don't want to kind of overload you with different error messages. But what we have here is something that could potentially be unsafe, because in this drop method for the node, we're dereferencing through to another garbage collected object. And because we say we're allowed to garbage collect through cycles, well, that could have been finalized ahead of time, right? Oh, sorry, before we get to this finalizer. So that's got the potential for unsoundness there. And so if I compile that, you see finalizer safety analysis has shown you an error, and it said, we're not going to run this program because this does something that might be bad. But what happens if you want the drop method to work as you would in your existing program? Lots of these drop methods would have been written in applications that never thought that GC would be used in the future. So if we remove any usage of those types from GC, what have I done here? Oh, I need to remove the call as well. This will compile fine because finalizer safety analysis only kicks in on types that are used in a GC in some way. The other thing as well I'll note is that if I put these back in, if we remove the problematic line and try and compile this again, this will work too. This will also traverse through function calls to a fixed point, because at the point that we do this, you have like a whole program analysis. Obviously, with things like externally linked stuff, this is not possible. But for the most part, we get pretty close. As I said, there's a lot of other things that can do, which we don't have time to discuss, but they're in the paper if you're interested. Yeah, if you want to talk about those things, come and see me. I'm more than happy to speak about them. I'm also going to be really shameless here and say that my postdoc is coming to an end. So I'm on the job market. If you need a compiler hacker, please hire me. Thank you.
We have time for a quick couple of questions.
So it looks a little bit like the drop check issues that you have in the past. So I guess the Rust has had in the past. So I guess I have two sort of related questions, which should be pretty quick. The first is, what is your analysis doing in the case of polymorphic types?
Yep.
And the second is, do you have any interaction with, for example, made angle attributes? Can I take something which wouldn't be a safe finalizer, I put made angle on there, and your analysis considers that?
With regards to your first question, where possible, we try and monomorphize those types. So this obviously can kind of have this like exponential blow up. So we have a sort of fixed point where we say we won't go further and we'll disallow this at this point. Sorry, what was your second question again?
The question was, does your analysis have any interaction with made angle attributes?
Yeah, so made angle attributes obviously create some trickiness around drop methods that our analysis looks at and says this needs to be manually verified by the programmer themselves. So no, we don't deal with that. It's up to it. We haven't really explored whether that's a space that's possible yet or not. But yeah, that's where we've got.
Thanks.
Cheers.
Okay, thank you again.